Yes, there is a limitation for cable length even if you maintain the same cable size after a tap. This limitation primarily stems from the concept of voltage drop, which is an important consideration in electrical systems. The National Electrical Code, or NEC, mandates that the voltage drop in a circuit should not exceed 5%. This means that if you start with a source voltage of, for instance, 120 volts, the voltage at the point of use or load must be at least 114 volts. This is calculated as 120 volts minus 0.5 times 120 volts, which equals 114 volts. Voltage drop is influenced by several factors. Firstly, the length of the cable. Secondly, the size or gauge of the conductor within the cable. And thirdly, the amount of current flowing through the cable. Longer cables inherently exhibit a greater voltage drop because the electrons have a longer distance to travel through the resistance of the wire. Similarly, smaller conductors, characterized by a higher resistance per unit length, result in a more significant voltage drop compared to larger conductors. Also, as the current increases, the voltage drop also increases proportionally due to Ohm's law. In scenarios where you are tapping into an existing cable and continuing with the same conductor size, the primary factor influencing voltage drop becomes the length of the cable after the tap. The NEC doesn't stipulate a specific maximum length for cable taps using the same size conductor. However, it does provide tables that specify the maximum allowable voltage drops for various cable sizes and current levels. These tables are essential for ensuring compliance and safe operation of electrical systems. For example, consider a No. 12 American Y-gauge or cable, which has a maximum ampacity or current carrying capacity of 20 amps under certain conditions. If this cable is 100 feet long and carrying its maximum rated current, the NEC might specify a maximum allowable voltage drop, let's say 1.5 volts. This would mean that at the end of the 100-foot run, the voltage must not drop below 118.5 volts, which is calculated as 120 volts minus 0.15 times 120 volts, equaling 118.5 volts. When tapping into a cable and continuing with the same size, it is crucial to ensure that the total length of the cable run, including both the original segment and the tapped segment, does not exceed the maximum allowable length dictated by the NEC tables for the given cable size and current. To determine the maximum allowable length for a specific application, you need to consult the appropriate NEC table. These tables typically provide voltage drop information based on conductor size, the type of conductor material, which is usually copper or aluminum, the installation method, which can be in conduit, free air, or direct burial, and the anticipated current flowing through the conductor. Using these tables, you can calculate the maximum length of cable that will maintain the voltage drop within the 5% limit. The calculation usually involves using Ohm's law and the resistance per foot of the conductor, which can also be found in NEC tables or other engineering resources. Remember that exceeding the maximum allowable voltage drop can lead to several problems, including inefficient operation of equipment, overheating of conductors, and potential safety hazards. Therefore, it is crucial to carefully consider voltage drop when designing and installing electrical systems, especially when dealing with cable taps. To elaborate further on voltage drop calculations, one needs to understand the fundamental principles governing electrical circuits. Ohm's law, expressed as voltage equals current times resistance or volts equals amps times ohms, is the cornerstone of these calculations. The resistance of a conductor depends on its material, which is typically copper or aluminum, its length, and its cross-sectional area, which is determined by its gauge. The resistance increases proportionally with the length of the conductor and inversely with its cross-sectional area. This means that a longer and thinner conductor will have a higher resistance than a shorter and thicker one. The NEC provides tables that list the resistance per foot for various sizes of conductors. These values are typically expressed in ohms per 1,000 feet, which can then be converted to ohms per foot for easier calculation. To calculate the voltage drop in a cable, you first need to determine the total resistance of the cable. This is done by multiplying the resistance per foot by the total length of the cable. Then, you multiply the total resistance by the current flowing through the cable to obtain the voltage drop, using Ohm's law. For example, let's say you have a 100-foot run-of-no 12 AWG copper wire carrying 15 amps. The resistance of no 12 AWG copper wire is approximately 1.588 ohms per 1000 feet. This converts to 0.1388 ohms per foot. The total resistance of the 100-foot run is 100 feet times 0.1588 ohms per foot, which equals 0.1588 ohms. The voltage drop is then calculated as 15 amps times 0.1588 ohms, which equals 2.382 volts. This means that the voltage at the end of the 100-foot run will be 2.382 volts lower than the voltage at the source. If the source voltage is 120 volts, the voltage at the load will be 117.618 volts, which is within the allowable 5% voltage drop limit. However, if the cable run were longer, or the current were higher, the voltage drop could exceed the limit. It's also important to consider the voltage drop in both the supply and return conductors. The calculations above are for one direction of the circuit. Therefore, in practice, you might need to double the calculated voltage drop to account for the entire loop. Voltage drop can also be affected by the type of load connected to the circuit. Resistive loads, such as incandescent lights and heaters, draw a constant current, making voltage drop calculations relatively straightforward. However, inductive loads, such as motors and transformers, draw a varying current, which can make voltage drop calculations more complex. In these cases, it's necessary to consider the power factor of the load, which is a measure of how effectively the load uses electrical power. A lower power factor means that the load draws more current than it actually needs, which can increase voltage drop. To mitigate voltage drop, several strategies can be employed. Firstly, you can increase the size of the conductor, which reduces its resistance. This is often the most effective way to reduce voltage drop, but it can also be the most expensive. Secondly, you can shorten the length of the cable run. This is not always possible, but it can be an effective way to reduce voltage drop in some cases. Thirdly, you can reduce the current flowing through the cable. This can be done by using more energy-efficient appliances or by distributing the load over multiple circuits. Another consideration is the type of wiring method used. Conduit, for instance, can affect the heat dissipation of conductors, which in turn affects their ampacity and voltage drop characteristics. Furthermore, the material of the conductor plays a crucial role. Copper is generally preferred due to its lower resistance compared to aluminum, but aluminum is lighter and less expensive. When using aluminum conductors, it's essential to use appropriately sized conductors and connectors that are rated for aluminum to prevent corrosion and overheating. The NEC provides specific guidelines for using aluminum conductors, including dirting factors and terminal connection requirements. In summary, when tapping into a cable and continuing with the same size conductor, careful consideration must be given to voltage drop to ensure that the electrical system operates safely and efficiently. By understanding the factors that influence voltage drop and using the NEC tables to determine the maximum allowable cable length, you can avoid potential problems and ensure compliance with electrical codes. Remember to consider the total length of the cable run, the size and material of the conductor, the current flowing through the cable, and the type of load connected to the circuit. By carefully planning and executing your electrical installations, you can minimize voltage drop and ensure the reliable operation of your electrical systems. Furthermore, regularly inspect and maintain your electrical systems to identify and address any potential voltage drop issues before they become major problems. This includes checking connections for corrosion or looseness, ensuring that conductors are properly sized for the load, and verifying that the voltage at the load is within the allowable limits. Proper maintenance can help to extend the life of your electrical equipment and prevent costly repairs. By following these guidelines, you can ensure that your electrical systems operate safely, efficiently, and reliably for years to come.